chemical reactions of amines. Chemical reactions of amines when we analyze. You see the nitrogen atom and connected hydrogen atom. They have considerable good difference in their electronegativity. And there is an unshared pair of electrons over nitrogen. Quite naturally, it acts as a good nucleophile. And the number of hydrogen atom attached, that also plays a vital role in case of the chemical reactions of amines. So primary amine, quite naturally, primary amine contain NH2, 2 hydrogen atom. Secondary amine NH, tertiary amine N only. So number of hydrogen atom attached definitely plays a vital role in deciding the characteristics. Quite naturally, primary, secondary, tertiary amine react in a different way. Okay. Amines can behave as a nucleophile as there is a lone pair of electron with the nitrogen, and they are bases also. That is our next point of discussion in the chapter, basic nature of amines. Basic nature of amines. Already when we started the chapter, it was commented. Hope you remember. Aliphatic amines are more basic than ammonia, while aromatic amines are less basic than ammonia. It was already commented, and that is a general comment. Aliphatic amines are more basic than ammonia, while aromatic amines, aniline, is less basic than ammonia. Why aromatic amines are less basic than ammonia? I don't have to tell you, all of you know. In case of aromatic amine, there is resonance. So due to resonance, the lone pair of electron with the nitrogen is withdrawn by the benzene ring. So the lone pair of electrons on nitrogen, when utilized for resonance in the benzene ring, the availability of lone pair of electrons decreases. Quite naturally, this is acting as a Lewis base, all of you know. Ammonia and ammonia derivatives acting as Lewis bases, presence of lone pair of electron is very important. Now, this lone pair of electrons, when withdrawn by the benzene ring for resonance, means it is less available, means it is less basic than ammonia. Right? And the pKb values establish that fact. Once again, when we discuss about acidic nature, we talk about Ka, pKa. For basic character, we talk about Kb, pKb. But that is in aqueous solution. So, greater the Kb value, greater the Kb value, lower the pKb value, stronger the base. That's a general point all of you know. Kb, pKb value can be taken as a function or measuring parameter for the basic strength. Greater the Kb value, lower will be the pKb value, stronger will be the base. Greater the Ka value, lower the pKa value, stronger the acid. Greater the Kb value, lower the pKb value, stronger the base. If you take ammonia, the pKb value is 4.75 something, while that of aliphatic amines will come down to 3.5 range. While for aromatic amine, it goes 9, 10 range. Try to understand. Okay. So anyhow, aliphatic amines will be more basic than ammonia, while aromatic amines are less basic than ammonia. And how comes the basic strength for primary, secondary, tertiary amine? For vapor phase, the strength of basic character decided mostly by I factor, inductive effect, and you can see in vapor phase, the order of basic strength will be tertiary greater than, secondary greater than, primary greater than ammonia, irrespective of which alkyl group it is present generally. Suppose you take aliphatic amine, tertiary aliphatic amine, whether you deal with the methylamine or ethylamine, whether it is methylamine or ethylamine, tertiary amines most basic. Tertiary amines most basic. You see that R, N, R, R. This is tertiary amine. The electron density over here will be maximum due to plus I effect of this group, due to plus I effect of this group, and due to plus I effect of this group. Therefore, tertiary greater than. What about secondary? There are two alkyl groups donating electron density, plus I effect of this group and this group only. What about primary? It is RNH2. Only there is one group for supporting with the inductive effect. So here we have three inductive effect of the three alkyl group. Here we have two inductive effect of the two alkyl group. Here we have only one alkyl group. So tertiary, secondary, primary ammonia. That is the order of basic strength in vapor phase, or even if you take in some aprotic medium, not necessarily in vapor phase. In aprotic medium, suppose you are taking in benzene or any other organic solvents, this will be the condition. Sir, then what about in aqueous medium? That also many of you already studied. What is in aqueous medium? In aqueous medium, multiple factors influences the basic strength. Suppose we take in aqueous medium, we have to consider the equilibrium involved there. RNH2 plus H2O giving RNH3 plus OH minus. This is what the equilibrium involved in aqueous medium, and you have to consider Kb value, which is RNH3 plus concentration into OH minus concentration divided by RNH3 quantity. This equilibrium will decide the basic strength of amines in aqueous solution. All of you know that. And that in fact, the value of Kb, greater the value of Kb means greater the quantity of this. Greater the quantity of this and stronger the base. A greater quantity of this means that is stable. So the stability of conjugate acid RNH3 plus decides the basic strength. Greater the stability of conjugate acid RNH3 plus, greater the basic strength of RNH2. So the basic strength of amines greatly decided by the stability of the conjugate acid. And the stability of conjugate acid decided by multiple factors. What are the multiple factors? Of course, I effect will be involved. Inductive effect will be involved. And you know, inductive, according to inductive effect, the privilege will be in this order: tertiary, secondary, primary. That will be the order according to inductive effect. Right? And steric factors are one other reason. Steric factors. Steric factors are one another reason. Steric factor means spatial crowding. So bulky groups will be greatly influencing their nature on stabilizing the system. Steric factors. So when we consider steric factors, the stability will be primary, secondary, tertiary in that way, because tertiary with the large bulkier, greater number of bulkier groups found to be less stable due to steric reasons, right? Now, there is another important factor, solvation effect. Solvation effect, which is greatly influenced by hydrogen bonding. Greatly influenced by hydrogen bonding. So whether solvation effect or effect of hydrogen bonding, it will be in the order primary, secondary, tertiary. Why primary, secondary, tertiary? Why primary get a privilege for solvation? Already discussed a few minutes back. The presence of hydrogen. There is RNH2. 2 hydrogen produces greater extent of hydrogen bonding in primary than in secondary, than in tertiary. So when you look at I effect, tertiary may dominate. When you look at the steric factor, solvation, another factors. So multiple factors in different way influences the stability of conjugate acid formed. Hence influences the basic strength of amines. And quite naturally it will vary from different kind of amines. You can't expect the order for methylamine and ethylamine to be same, because methyl is a relatively smaller group, ethyl is a relatively larger group. That of course is going to put a different kind of inductive effect as well as steric effect. So all these cumulated, collaborated effect of multiple factors, all these cumulated effect contributed by multiple reasons, multiple theoretical justifications. We see that the order for methylamine and ethylamine and other amines may be different. For methylamine, the order expected is, order observed is, for methylamines, the observed order is secondary greater than, tertiary greater than, secondary greater than, primary greater than, tertiary greater than ammonia. That means CH3 twice NH secondary greater than CH3 NH2 primary greater than CH3 thrice N tertiary greater than ammonia. This is the order observed for methylamines. So maybe considering I effect a tertiary maximum, maybe considering solvation effect a primary maximum, considering all different kind of influences taken together, it is observed experimentally with the Kb value, with the pKb value, that secondary comes first, then primary, then tertiary. That is the order according to the observed pKb values. Is it same for ethylamine? No, it is not same for ethylamine. If you take ethylamine, the order is different. For ethylamine, the order is, of course, secondary greater, then tertiary, then primary, then ammonia. That is the order for ethylamine. That means C2H5 twice NH maximum, then C2H5 3 times N next, and C2H5NH2 next, and then ammonia. That is the order for ethylamine. So for ethylamine, there is a small difference, of course, secondary maximum, then primary, then tertiary, secondary, tertiary, primary. Okay. And you can easily memorize for methyl. Methyl means a small group. It is small number 213. For ethyl, a bigger group, a bigger number 231. Memorize that to memorize the order of methyl, ethyl amines in aqueous solution. While in vapor phase or in some aprotic solvents, the order remains same. For methyl and ethylamine, it is tertiary, secondary, primary. So this will be the order. This will be the order if you take in vapor phase, and we don't mind it is methyl or ethyl. But in aqueous solution, the order found to be different. For methylamine, this is the order. For ethylamine, this is the order, considering a cumulative effect of multiple reasons, like I effect, steric factors, solvation effect, etc. Hope you get the point. Okay. Multiple times the questions came based on the order of methyl, ethylamine, and don't forget 213 will be for methylamine, 231 for ethylamine. Methyl small group, small number. Ethyl bigger group, bigger number. Memorize like that. So maybe in future they are going to ask combined methyl and ethyl. Combined they may ask. Combined they may ask. Very simple, no? This is methyl 2, 1, 3. This is methyl. Secondary, primary, tertiary. That is for methyl. And what about ethyl? What about ethyl? It is secondary, tertiary and primary. This is the order for methyl. Okay? Okay? Now, what you can understand, the order combined effect, combined order for both, how we can memorize is, it will be like this. It will be like this. You may memorize like this. You see, this is methyl and this is methyl and this is ethyl. Methyl order combined with ethyl, this will be the order. This will be the order. This is ethyl and this is methyl. So what is the order? Secondary ethyl, greater than tertiary ethyl, greater than secondary methyl, greater than primary ethyl, greater than primary methyl, greater than tertiary methyl, greater than ammonia. That way you can memorize. Hope you get that picture clear. Put it exactly in your mind with the pictorial identity, which will help you to understand or recollect easily during the exam time. So it is 2, 3, 2, 1, 1, 3. That is secondary ethyl, tertiary ethyl, secondary methyl. So secondary methyl comes one step ahead, that's all. Primary ethyl, primary methyl, say tertiary methyl. So you have 2, 3, 1, put the methyl 2 just ahead, that's it. That will be the order according to pKb values, according to the experimentally observed values, pKb values. Is that okay? Fine? Good. So all these are clearly demonstrated with their pKb values in the textbook, which you can easily identify how their order comes, or is it matching with the what order what I said. This is methenamine primary, this is N-methyl methenamine secondary, N-dimethyl methenamine tertiary, that is methyl, and this is ethanamine primary, this is ethanamine secondary and ethanamine tertiary. Hope you find the minimum pKb value here, secondary ethyl, then it is tertiary ethyl, isn't it? Then it is secondary methyl, then it is primary ethyl, then it is primary methyl, then it is tertiary methyl, where ammonia it is 4.75, that will be after this. While if you go to aniline, while if you go to aromatic amine, you can find it is 9.38, high pKb value, least basic. While we have phenyl methenamine coming 4.7, this somewhere in this range. Why? Phenyl methenamine is not in fact aromatic, that's why. Phenyl methenamine is not aromatic. This is phenyl methenamine. The amino group is not directly connected to the benzene ring and is not involved in resonance. So quite naturally you see the difference here, 9.38, here it is 4.7 only. While these are all aniline, secondary aromatic, N-methyl aniline value slightly decreases due to the methyl group. N-dimethyl aniline value again slightly decreases due to 2-methyl group, like that. So a detailed order available regarding the pKb values of various aliphatic aromatic amines. Now what about the effect of substituents? What about the effect of substituents on aromatic amines? When you look at the effect of substituents on aromatic amine, this is aniline. This is aniline compared with toluidine. Compared with toluidine. And compared with nitroaniline. Aniline, toluidine, nitroaniline. I don't have to tell you, I believe, what will be the effect of basic strength on amines with the substituents. As we were discussing similar content in acids for benzoic acid, electron withdrawing group increases the acidic character. Here electron withdrawing group decreases the basic character. So this is electron withdrawing group. This is electron withdrawing group. So the lone pair from nitrogen will be withdrawn by NO2. That means the electron density here will decrease. Right? So this will be less basic, while this is electron donating group, and therefore electron density over here will increase. So the order will be, if this is 1, this is 2, this is 3, the order will be 2 greater than 1 greater than 3. This will be the order. This is highest, then this, and then this. That will be the order. So against what we discussed in benzoic acid, where electron withdrawing group increases the acidic character, here electron withdrawing group decreases the basic character. There electron donating group decreases the acidic character. Here electron donating group increases the acidic character. Okay. And there we have discussed one important point. Presence of any group coming at ortho position. Hope you remember. Presence of any group coming at ortho position. This is benzoic acid. Any group coming here, whether it is electron donating group or electron withdrawing group, maybe electron donating group or electron withdrawing group present at ortho position, the acidic character shoot up, the so-called ortho effect. Ortho effect. The acidic character shoot up. While coming to this point regarding aniline, it will be just opposite. There is ortho effect. Any group X, whether it is electron withdrawing group or electron donating group present at ortho position, you can see the basic character drops and is again called a ortho effect. So due to ortho effect in benzoic acid, acidic character increases. Due to ortho effect in aniline, basic character decreases. What is the reason? No one point of reason. There can be multiple reasons like electronic effect, like steric effect, steric inhibition effect, solvation effect. Multiple reasons will contribute. Altogether, hydrogen bonding, intramolecular hydrogen bonding possibility. Multiple reasons will contribute towards the ortho effect. Ortho effect applicable in aniline and benzoic acid. And there we come to an end of basic strength of amines, a very important topic from the chapter. Just like what we discussed, acidic strength in benzoic acid, acidic strength in carboxylic acid, acidic strength in alcohol, phenol, ether, alcohols and phenols. Just like that, the basic strength properties of amines, very important topic. Clear? Fine. A detailed explanations of this is available. And now about alkylation. Alkylation already detailed discussed earlier few minutes back. It is alkylation, Hoffmann's alkylation, Hoffmann's exhaustive alkylation, Hoffmann ammonolysis, etc. and including Hoffmann elimination that we have discussed in the classes. A detailed note is given, already discussed. Next is acylation reaction. Acylation reaction. Acylation reaction. See how acylation take place with the amines. Acylation reaction with the amines. Have a close look at. We have example ethanamine. We have example ethanamine interacting with the acyl chloride. So this is a nucleophilic center, will attack over C plus as it polarizes as C plus and O minus. C plus attacked by nitrogen. And now what happens? This Cl, this bond is breaking out as Cl minus and this as H plus, HCl out. HCl out. And you get C2H5 NHCOCH3. You get N-ethyl ethanamide. N-ethyl ethanamide. Acylation reaction. Acylation reaction. Here you have acylation of secondary amine. This is primary amine giving acylation N-ethyl ethanamide. This is secondary amine acylation, you get N-diethyl ethanamide. N-diethyl ethanamide. And the overall reaction can be understood like this. Overall reaction can be understood like this. RNH2 is attacked with the CS3COCl. CS3COCl. This is CS3COCl. You see, this is polarizing as minus and plus, and this nucleophile attacks here. You get the result RNHC O minus ClCH3 like this. Now this is out as Cl minus and this will be out as H plus and Cl minus out as HCl. You get RNHCO COCH3. You get N-alkyl ethanamide. N-alkyl ethanamide. Okay. What about if it is a secondary amine? What about if it is a secondary amine? RNRH. Same way. What do you get? It is polarizing minus and plus, and this nucleophile will attack over here. You will get RNRH CO minus ClCH3. Now this Cl out as Cl minus and this H out as H plus, HCl out. And what is the result? The result will be, you get RNRCOCH3. You get N-dialkyl ethanamide, secondary amide. Is it clear? In fact, tertiary amide. You get the amide. That is acylation reaction. There is benzoylation reaction. There is benzoylation reaction. How comes benzoylation reaction? Benzoylation reaction. You see that RNH2 with the benzoyl chloride. Benzoyl chloride. You can easily understand the reaction is like this. HCl out. HCl out. You get RNH CO benzene ring. You get N-alkyl benzamide, N-alkyl benzamide, benzoylation, benzoylation. Benzoylation of aniline, benzoylation of phenol, very popular, called Schotten-Bowman reaction. Benzoylation of aniline. Look at aniline undergoing benzoylation. Look at aniline undergoing benzoylation. You see, this is HCl out. And what do you get? You get N-phenyl benzamide. N-phenyl benzamide. This is N-phenyl benzamide. There is similar reaction with the phenol. There is similar reaction with the phenol. This is reaction with the phenol. And is benzoylation reaction. Benzoylation reaction. And is very popular, called Schotten-Bowman reaction. HCl out. HCl out. You get this one. You get an ester. You get an ester, phenyl benzoate. Phenyl benzoate ester. Whether this or this, that is benzoylation reaction, very popular, called Schotten-Bowman reaction. Schotten-Bowman reaction. So, acylation reaction, benzoylation reaction, Schotten-Bowman reaction applicable to aniline as well as phenol taken for benzoylation, right? Yes. That is what delta over these regions. Then there is another very famous reaction, Carbylamine reaction. Carbylamine reaction. What is Carbylamine reaction? This is Carbylamine reaction, so-called isocyanide test. Carbylamine test. Isocyanide test. Carbylamine test. It is given by primary amine. It is given by primary amine treated with the chloroform alkali. Primary amine treated with the chloroform alkali. You get a foul smelling product which is alkyl isocyanide called carbylamine. Carbylamine. It's a test for primary amines. It's a test for primary amine. Any primary amine given to you, you add some chloroform, add some KOH, you are getting a foul smelling product that can be taken as a confirmatory test for primary amine. Okay. Let's see the story behind the reaction. Let's see the story behind the reaction, that is mechanism involved. What is the mechanism involved? You have chloroform. You have chloroform which is interacting with the KOH, which is interacting with the KOH, OH minus and H plus out as water. OH minus and H plus out as water, and thereby you get like this. You get like this. Immediately it is out as Cl minus with the K plus out as KCl, and you get the very popular intermediate, active intermediate dichlorocarbene. You get dichlorocarbene, that is the active intermediate obtained when chloroform interact with the alkali. Now this is a electrophile, all of you know. This is an electrophile, seem to be like a nucleophile, but it is electrophile having electron deficit system. 2 electron here, 2 electron here, 2 electron here. It is only 6 stet. not having octet. Therefore, it will be attacked by ammonia. The primary amine will be attacking this dichlorocarbene, and thereby you get the result RNHHCl2 like this. You get like this, right? Again, it is interacting with the KOH. It is interacting with the KOH. Now you see K plus and Cl minus out as KCl, and OH minus with the H plus out as water, and the result will be NH double bond CCl like this. You get like this. Fine. Yes. Now the same story will repeat again. The same story will repeat. You can see K plus and Cl minus out as KCl, OH minus and H plus out as water, and you get the final product that we are talking about. The final product obtained will be RNC. This is what the final product we get, which is carbylamine, which is isocyanate. And that is the story behind carbylamine test, which is answered only by primary amine according to this script. Hope it is clear to all. Fine? Good. So is that matching with the balanced final equation? We have one primary amine, one chloroform, 3 KOH, one over here, and one over here, giving RNC 3 KCl, 1 KCl over here, 1 KCl over here, 1 KCl over here, and 3 H2O, 1 H2O, 2 H2O, and 3 H2O. Balanced. Fine? Good. Next, reaction with the nitrous acid. Reaction with the nitrous acid. All of you may be remembering aliphatic primary amine. If you take aliphatic primary amine treated with the nitrous acid, that is NaNO2HCl, you get aliphatic diazonium salt. Aliphatic diazonium salt is highly unstable even at a low temperature. Even at a low temperature, aliphatic diazonium salts are unstable, and immediately it is hydrolyzed to alcohol, expelling nitrogen gas. So aliphatic primary amine, when treated with the nitrous acid, you get a diazonium chloride, which is immediately converted to alcohol, liberating N2 gas. And that in fact is very important. Quantitative evolution of nitrogen is used in estimation of amino acids and proteins. So how many amino acids, how many amino groups are present that you can estimate with this reaction? Amount of N2 gas liberated can be quantitatively used as an estimation procedure for amino groups in proteins. Okay. So what do you get if you take ethanamine? If you take C2H5NH2 when treated with nitrous acid, final result will be C2H5OH, expelling nitrogen gas. What is actually happening? You get ethylamine converted to ethyl diazonium salt, which is unstable and hydrolyzed to ethanol. Clear now? And what about aromatic amine? Aromatic primary amine, say aniline, undergoing reaction with the nitrous acid HCl, you get benzene diazonium chloride, which is stable at a low temperature, 0 to 5 degrees Celsius, 273, 278 Kelvin. It is stable, and it can be utilized for various other reactions as We have learned in detail Sandmeyer's reaction, Getterman reaction, sorry, not Getterman reaction, Sandmeyer's reaction, Bal-Schiemann reaction, various synthetic productions related. We are using, of course, we are discussing coupling reactions, various production of various azo dyes and all. Benzene diazonium salt, which is found to be stable at a low temperature, can be used for synthetic purpose of related compounds like Sandmeyer's reaction and other related reactions. Aromatic primary amine. So aromatic diazonium salt is stable at a low temperature. That too is stable only at a low temperature. If you warm it, it will be converted to phenol, all of you know. So at a low temperature, this group will be stabilized by the resonance given by benzene ring. That's why it is stable at least at a low temperature. So aliphatic primary amine, you get diazonium salt converted to alcohol. Aromatic primary amine stable at a low temperature and can be used for other reactions like Sandmeyer's reaction. Right? While NCERT is making a comment, secondary, tertiary amines react with the nitrous acid in a different manner, and we have given a detailed note regarding that in the classes. How secondary aliphatic amine and secondary aromatic amine react uniquely. Secondary aliphatic and secondary aromatic react in a similar way and the product obtained is similar. You get a yellow oily nitroso product. Notes are given. While tertiary aliphatic amine, you get a nitrite salt. Notes is given. Please review that. While tertiary aromatic, N,N-dimethyl-aniline, you get para-nitroso product. That is also not given. So even though simply commented in the textbook, secondary, tertiary reacting in a different way, a detailed study was done and detailed notes were given in the classes. Please review that note, in which you will remember, maybe secondary aliphatic aromatic, same way it reacts. You get a yellow oily nitroso product. While tertiary aliphatic, you get a nitrite salt. Tertiary aromatic, you get a para-nitroso product. Right? Good. Next is Hinsberg reaction. Next is Hinsberg reaction. Reaction to detect primary, secondary, tertiary amine. Hinsberg reaction using Hinsberg reagent. Reaction with aryl sulfonyl chloride. Reaction with benzene sulfonyl chloride called Hinsberg reagent. A test for primary, secondary, tertiary amines. A test for primary, secondary, tertiary amines. Hinsberg test using Hinsberg reagent. Benzene sulfonyl chloride. This is benzene sulfonyl chloride, the so-called Hinsberg reagent. Hinsberg reagent. This can be utilized for testing primary, secondary, tertiary amines. Let's see how this can be used for testing primary, secondary, tertiary amines. Suppose we are dealing with primary amine. Suppose you are dealing with a primary amine. This is a primary amine. See how the reaction takes place. HCl out, like what we were discussing in benzoylation, acylation. HCl out, and what is the result? You get N-phenyl benzene sulfonamide. N-phenyl benzene sulfonamide. N-phenylbenzene sulfonamide, which will dissolve in alkali. It will dissolve in alkali forming a salt. Dissolve in alkali forming a salt, as there is a acidic hydrogen present. So we have two hydrogen present here. In fact, a few minutes back when we started, it was commented number of hydrogen plays a vital role in the reactions. So there are two hydrogen available here. One of the hydrogen involves in acylation. You get this N-phenylbenzene sulfonamide, which dissolve in alkali. As there is one hydrogen present, you get a salt. This will be primary amine. What about secondary amine? What about secondary amine? If you take a secondary amine, look at the reaction. This in fact is a secondary amine. It undergo HCl out as we were discussing acylation or benzoylation, and you can see the result. This is the result. And that is NN dialkyl. NN dialkyl benzene sulfonamide. I don't have to tell you, this is insoluble in alkali. Why it is insoluble in alkali? Here you had an acidic hydrogen, therefore dissolves in alkali. Here you don't have acidic hydrogen, therefore it is insoluble in alkali. So primary amine react with the Hinsberg reagent, you get a solid product which dissolve in alkali forming a salt. While secondary amine react with the Hinsberg reagent, you get another solid product which is insoluble in alkali. What about tertiary amine? What is the nature of tertiary amine? Tertiary amine, very simple to understand, will not react with the Hinsberg reagent. This is Hinsberg reagent and this is tertiary amine. This is tertiary amine. It's quite simple to understand, there is no reaction as there is no hydrogen present. Isn't it? So primary amine reacting with the Hinsberg reagent, you get a solid product N-alkyl benzene sulfonamide which dissolves in alkali due to the presence of hydrogen here. Secondary amine react with the Hinsberg reagent, you get NN dialkyl benzene sulfonamide which will not be soluble in NaOH, and tertiary amine no reaction at all. This is Hinsberg test. Okay. And in fact, there is a comment you might have noticed in the textbook. There is a comment given. These days, benzene sulfonyl chloride replaced with para-toluene sulfonyl chloride, tosyl chloride. Tosyl chloride is used in Hinsberg reagent to get a better effective reaction. This is the reagent. Please keep it in your mind and don't mess up once you see this for the exam. It is there in NCERT. Para-toluene sulfonyl chloride. The presence of a electron donating group will give a better result in the reaction. Para-toluene sulfonyl chloride, tosyl chloride. Tosyl chloride used in place of in Hinsberg reaction. That also, if you find such a reagent for the exam, don't get messed up. It is there in the NCERT. Okay, that's it. So that's about carbylamine test. That's about reaction with the nitrous acid. That's about Hinsberg reagent, Hinsberg test. Okay. Next is ESR, electrophilic aromatic substitution reaction. ESR, electrophilic aromatic substitution reaction. See the ESR reaction for aniline. ESR reaction for aniline. The NH2 group in aniline. It is ortho and para directive. Ortho and para directive. And there is high electron density. NH2 group is activating group. NH2 group is electron donating group, activating group, ortho para directing group. There will be a greater electron density at ortho para positions. And if you go for bromination in aqueous medium, bromine water, when you deal with, you can see you are getting a white precipitate 2,4,6 tribromoaniline. A clear indication like what we seen in phenol. It is highly reactive. It is highly reactive. All ortho-para positions substituted by bromine, you get a 2,4,6 tribromoaniline, a white precipitate. Clear? And what do you do if you want to get a mono substitution product? What you do if you want to get a mono substitution product? You want one bromoaniline. You want aniline converted to, monobromoaniline, parabromoaniline, or one substituted aniline, monobromo substituted aniline. What do you do? That in fact is one of the major point of discussion in this area. What we can do is aniline treated with acid anhydride, aniline treated for acylation. Aniline when treated for acylation, you will get acetanilide. You see this acyl group is introduced over here. You get N-phenyl ethanamide. N-phenyl ethanamide. Now you can see this is highly activating group, and now the activating effect of NH group is suppressed. How suppressed? The electron density in nitrogen is withdrawn by CO group. You see that due to resonance. Look at this. Due to resonance, electron density is nitrogen withdrawn by CO group, and you get a partial positive center on nitrogen. Nitrogen turn a positive center due to resonance. That means electron density over nitrogen will be suppressed. That means the activating effect of nitrogen is suppressed. And now when you conduct the bromination, bromine comes not at all position 2,4,6, rather it comes at one position, para-bromo product. You get para-bromo acetanilide. Now the service of this group is over. You just take for hydrolysis. When you hydrolyze, this group will be out, and you get the aniline back. You get 4-bromoaniline. This is called a protective bromination, controlled bromination. So by controlled bromination, by protective bromination, you can bring in one bromine in the ring substituted. How you protect? You protect by acylation. How by acylation it is protection happening? The NH2 nitrogen electron pair is withdrawn by the nearby CO group. Thereby, activity of nitrogen is somewhat suppressed. Is it clear? Yes. Same way we do nitration also. Same way we do nitration also. Protective nitration. Protective nitration we do the same way. Not this one. Protective nitration. You see, aniline when treated with acetic anhydride, you get acetanilide. So the electron density over nitrogen will be withdrawn by CO group, and the activating effect is controlled. Now you go for nitration, you get NO2 comes at para position. And now the service of this is over. You get a para nitroaniline by hydrolysis. So mononitration product you can get by the same method. It is called a protective nitration. What happens if you do the nitration normally? That's an interesting story. What happens when you do the nitration normally? When you do the nitration normally, this is what happening, and it's quite interesting story. I think all of you are gone through this, right? When you take aniline taken for nitration, it is a strong acid medium. A strong acid medium will protonate NH2 nitrogen. NH2 nitrogen group is getting protonated in strong acid medium, and thereby NH2 becomes NH3 plus. NH2 is orthopara-directing, but NH3 plus is meta-directing. Not quite surprisingly, 47% of meta product you get. In fact, in aniline taken for ESR, we are expecting orthopara product because NH2 group is activating group, electron donating group, orthopara directing group. But in fact, when you go for nitration or any such situation where strong acid medium is involved, you may get meta product. Not a small amount. You see, 51% of para, 2% only ortho, while 47% meta. So major product is para product. Okay, fine, good, as usual. But ortho product is only 2%. In fact, meta product 47%. Because there is a significant amount of protonation happening over here, and that makes NH2 act as NH3 plus. Hence you get meta product. Not a small amount, but a reasonable good amount. That's a very interesting story regarding the nitration of aniline. And if you want to get major para nitro product, what you can do is, as I said, protective nitration is best. You protect amino group by acylation and then do the nitration, you get a para nitroaniline in a good reasonable quantity. That's about aromatic electrophilic substitution reaction. And now we have another interesting one is sulfonation. Sulfonation. You see, aniline treated for sulfonation. Aniline treated with the sulfuric acid, sulfonation. You get a neutralization. This is the base, this is an acid. You get a neutralization. Anilinium hydrogen sulfate. Anilinium hydrogen sulfate. And now the story is, when you heat it slightly, you get there is a rearrangement happening and you get sulfanilic acid. Sulfanilic acid. What is sulfanilic acid? Para amino, 4 amino, benzene sulfonic acid. 1, 2, 3, 4. 4 amino benzene sulfonic acid, which can exist as a Switter ion. Because here you have an acid group, here you have a basic group. It can undergo self-neutralization. This is neutralizing to get SO3 minus and this is neutralizing to get NH3 plus. You get a Switter ion. What is Switter ion? Dipolar. Internal salt. Internal salt. Dipolar. Switter ion. Clear? And that region, that particular area completed with one vital important point. Aniline does not undergo FC reaction. Aniline does not undergo FC reaction, Friedel-Crafts alkylation and acylation due to salt formation with the aluminum chloride, which is used as a Lewis acid. Due to this, nitrogen on aniline acquire a positive charge and also acting as a strong deactivating group also. So the presence of Lewis acid makes aniline does not give Friedel-Crafts alkylation and acylation. Clear? because amino NH2 group is basic group. Lewis acid will interact with them directly and nitrogen will get a positive charge and hence it deactivates the reaction.